But before we actually start looking at some psychometric theory, we need to introduce the notion of measurement. What is measurement? And this whole idea was proposed by Dr. Stevens in 1940s. Stevens's definition of measurement is very simple. Measurement is a procedure of assigning numbers to mental objects in a way that relationship between the numbers represents the relationship between the mental objects. That's why it's called representational theory of measurement. Imagine that I'm developing a scale of subjective perception of how tasty different foods are. And I give you an answer scale from 1 to 5, and I say, could you please evaluate this piece of rye bread? And you say, okay, maybe it's 2. And maybe this pickled cucumber, okay, maybe it's 2 as well. And what about this wonderful cake? And the cake will be maybe 4, who knows? But then I say, okay, well, it means that probably the difference between a cake and a cucumber is equal to the taste of bread. So maybe if I add together a bread and a nice cucumber, I can get a sandwich that will be equally tasty as the cake. But you can say, no, nothing of the kind. If you add bread to cucumber, it doesn't become as tasty as the cake. And that's where we face this problem. Because not every operation that we can apply to numbers representing some mental objects is equally meaningful or equally applicable in relation to the mental objects that they represent. So for tastes, the scale might not be as straightforward. And here, we need to introduce the definition of a scale. The mathematical definition is a bit weird. A scale is a set of numbers that is isomorphic, which means it has the same properties as a set of empirical mental objects. For example, subjective sensations or attitudes or emotions or whatever it is. An easy definition for psychologists is that scale is basically a set of numbers plus a set of limitations concerning what we can do with those numbers meaningfully, given the nature of objects that they represent. So basically a scale is a set of numbers plus a set of rules that we need to apply to those numbers. And it was Stanley Stevens who proposed this classical distinction between 4 levels of measurement or 4 types of measurement scales. Each level of measurement involves a different set of assumptions about the relationships between the objects. The most simple, the most basic level is called nominal scale. In a nominal scale, the only relationship is that of equality. Is it the same or is it different? Imagine that I give you 5 different colors and I ask you to report your favorite color, and red is 1, yellow is 2, green is 3, and so on. And you give me an answer, for example, 2. And another person also gives 2. And I can compare those numbers and I can say, okay, you like the same color. Or if your numbers are different, I can say you like different colors. But there is nothing else I can conclude. I can only say same or different, because there is no quantitative relationship between those measured objects. The second type of scale, or the second level of measurement, is called ordinal scale, or ordered categorical. In addition to equality, there is also a relationship of order between the objects that we are measuring. So for any pair of objects, we can say which one is higher, which one is lower, which one is bigger, which one is smaller, and so on. Imagine that I ask you to report your education level. Is your education primary, secondary, or high education? And I can code them with numbers like 1, 2, and 3. The only thing I can be sure about is that if you say 2, if your education is secondary, it is higher. You've received more schooling than people who only have primary education, which is 1. But the question, how much? And that already is not so clear. Because maybe you received 5 years in addition if you left the school after 9th grade, or you received 7 years in addition if you studied the whole 11 years, or maybe 12 years in your country, or whatever it is. So for every individual, this difference can be different. But I can only be confident that which one is higher. A more extreme example comes from children. Imagine Sally, who is 5 years old, and John, who is 4 years old. But how large is the difference between Sally and John? It can be as small as 1 day in age, or it can be as large as 364 days. So for every pair of children, I can tell which one is older, but I cannot tell how much older. That is ordinal scale. An interval scale is a scale when we have, in addition to equality and order, we have a unit of measurement. We can say that a difference of 1 unit on the scale is constant across the scale. Imagine the temperature scale. If water has temperature 20 degrees Celsius and you want to heat it to 30, you would need the same amount of warmth, the same amount of energy as to heat it from 10 to 20, for example. But there is no absolute zero on this scale, because the 0 Celsius corresponds to some non-zero amount of energy in the matter. And it is basically an arbitrary point chosen comfortably for us to match the point of melting water. But the amount of energy is non-zero. As a result, you can be confident that equal increase in terms of degrees corresponds to equal increase in terms of energy. But you cannot ask the question how many times more. A water that is 20 degrees Celsius is not twice warmer than a water that is 10 degrees Celsius. There is a difference in the amount of energy, but it's not 2 to 1. If you want absolute zero, you need a ratio scale, where in addition to equal interval, equality and order, you also have ratio equality, or you have an absolute zero. For example, Kelvin scale of temperature. There is an absolute zero which corresponds to a zero amount of energy in the matter. And you can be confident that a matter that is 10 degrees Kelvin has twice less energy than something that has 20 degrees Kelvin. But if you want to convert it to Celsius or Fahrenheit, some interval scales, you would need to apply some additional conversion procedure. So these are 4 levels of measurement, and every time you deal with some kind of measurement, you need to be aware what kind of scale are you dealing with, because even when you enter your data in SPSS, you have a choice: nominal, ordinal, or scale. Interval or ratio, it doesn't really matter for SPSS, but at least those 3 levels you need always to be very clear about, because based on this information, SPSS decides what it can or cannot do with your data. And sometimes you can represent the same data, you can represent the same results using different measurement levels. For example, imagine a bunch of people are running a marathon. You want to represent the results of a marathon. And you can just record everyone who managed to complete the marathon and did not give up. So you will have just a list of numbers on their t-shirts. Or you can record people who came first, second, third, and so on. In this case, you will have rank order. If Sally arrived first and John arrived second, we know that Sally arrived quicker than John. But how much quicker? We don't know. Maybe the difference is 1 second, or maybe 10 minutes. An interval scale would be asking judges to give some kind of performance rating on a scale from 0 to 10 to every runner. And as a result, you will get some kind of performance rating. But there probably will not be an absolute zero, because a zero rating would, maybe it won't even be available on your scale, or maybe it will not correspond to absolute zero effort spent running. If you want a ratio scale, you can record how much time it took for every person to complete the marathon. So for every person, you will have time in minutes, measured with very high precision, and then you can say how many times quicker did Sally arrive than John, for example. So depending on your measurement level, there are different things that you are allowed or you can do with your data without screwing up the relationships between the objects represented by the numbers. If you have a nominal scale, you can do with it basically whatever you want. If your favorite colors are coded from 1 to 5, you can replace those numbers with any other numbers. -20, -1, 50, 71, whatever it is. You can even use irrational numbers like p or fractions and so on. As long as the same color is always coded with the same number, you're safe. With ordinal scale, it's a little bit more tricky because there is also order. So you can apply any monotonous increasing function, which can be nonlinear. But it's supposed to be monotonous, so it's supposed to be always increasing. For example, you have levels of education coded 1, 2, 3. You can change this to 4, 5, 6. Doesn't matter, the order is still the same. Or you can take a square root. Instead of 1, 2, 3, you will have 1, 1.4, 1.7, and so on. This is also fine, because a larger number corresponds to higher level of education, and it doesn't really matter what those numbers are, because all you care about is order. With an interval scale, which we encounter most often in psychology, the situation is a bit more complicated, because you can only apply linear transformations. If you have scores on an IQ test, you can add some constant to those scores, no matter. Or you can divide those scores by some number. It does not change the nature of measurement, because the difference between different individuals will still be expressed in the same unit, even though the scale of this unit will change. So basically, when we convert our raw scores to z-scores, we do a linear transformation. We subtract and we divide. But you cannot apply nonlinear transformations, because the intervals will change in a non-equal way. So for example, if one person has a score of 1, another 2, and another 3, the difference between 1 and 2 and 2 and 3 is equal in terms of how much psychological property contributes to this difference, or how many tasks did they solve. But if you do a square root, for example, you screw it up. Your unit will change to a different extent across the scale. So don't do it with an interval scale. It will become ordinal. And with ratio scale, you can do even less. You can only multiply or divide it, and ideally by a positive number, or you can flip it around. So a permissible transformation is a transformation of numbers that keeps the properties of relationships between numbers and objects. And what those properties are depends on what relationships are there in your scale. And why do we discuss this in such detail? Because in psychology there was a lot of controversy around this issue of permissible statistics. According to Stevens's classical view, we are only allowed to use those statistics where the result would be constant under any permissible scale transformations. So basically, depending on your type of scale, depending on your type of distribution, depending on what you know about the nature of the things that you are measuring, some statistics will be allowed and some will be not allowed. But already by 1960s, there were people who rebelled against this view, because they realized that there are many situations when we measure things, but we don't really know what is the nature of the thing that we are measuring and what are the real properties of those objects that our numbers represent. And maybe those objects even don't exist if we are measuring some kind of hypothetical construct and not just some subjective sensations that are kind of different. So even those statistics that are not permissible according to Stevens may sometimes be actually quite useful. Supes and Zins propose this abstract example. Imagine that you have two teams of football players, and all football players have numbers on their t-shirts. Oops, I have a typo on my slide. And Stevens would say, don't calculate mean score or don't calculate median. It is meaningless because the scale is nominal. But Siups and Zins would say, okay, but if for some reason you want to compare the sets of numbers, you can calculate a mean score. Maybe if in your particular context it makes sense to you, why not? So the controversy is whether our measurement should always maintain this exact relation to empirical facts or not. And Stevens believed that yes. So if you are measuring intelligence, you must first prove that intelligence exists and what kind of quantitative characteristics it has, and then you can prove how your scale reflects them. Unfortunately, in many cases, it's basically impossible. If we measure intelligence, and if we try to apply Stevens's paradigm, probably we would have to just abandon the whole idea. That's why psychometricians, such as Lord and Novick and others, they proposed another approach, which they called operationalism. Basically, support for our measurements comes not from our proof of the nature of what we are measuring, but it comes from relationships between different measurements. So if you have 5 different tests that all claim to measure intelligence, if the correlations are very strong, you can say, okay, they all measure the same thing. And even if you don't know what this thing is, numbers don't know where they came from. If the results of measurement are useful, if they correlate with some other characteristics that are important, and if the relationships between measurements are theoretically predictable, you're fine. And it's from here that this definition appears. Intelligence is what is measured by intelligence tests. Even though we don't know what it is still very useful. And there is also some classical approach, which is kind of more moderate, tries to make a compromise between the two, that probably there is some objective reality that corresponds to intelligence, maybe like the speed of a signal within the brain or individual differences in the structure organization of some nervous system. So when we measure intelligence, we kind of evaluate the magnitude of that quality, but we don't yet know what this quality is. So in the two latter approaches, our meaningfulness comes from empirical support for theories describing the relationships between our measurements, but not from our theory of measurement itself. Why is this even important for us? Because in practice, there are many debates in psychology. For example, maybe you have encountered in your previous studies a debate around normality issue. People who follow Stevens's paradigm, they say, first, you must always show you have a normal distribution, and only then you can calculate means and standard deviations. And if your distribution is not normal, you must use non-parametric statistics. But this view is kind of too extreme. At least most people in the scientific world would say that probably we need to have a more flexible point of view, because we need to acknowledge that data are never perfectly normal. There are always some deviations from normality, and it depends how strong these deviations are and what are the consequences. Will these deviations bias our parametric estimates or not? So we need to just quantify how strongly our distribution deviates from normal and be aware of this when we apply parametric statistics, be aware of the consequences. So you're allowed to apply parametric statistics even if the distribution is not perfectly normal and some Kolmogorov-Smirnov test is significant. So you may encounter still people who adhere to Stevens's point of view in the scientific community, especially in this country, because it's a bit more conservative, I guess. But we need to remember that Stevens's approach is great, but it's not always possible to implement in practice. Nevertheless, whenever you are measuring something, you always need to know what kind of level of measurement you have, what kind of scale you have, in order to make the right conclusions based on your numbers to apply the right statistics.